that working. Okay. I feel like I need to get one of those smiley face balloons and just attach it right to the top of the camera so it actually looks like I'm looking at a face. Because my default has been to look at the monitor, and that's where I see your chat messages, so I do need to look there, but focus on the camera. All right, you heard the lady. Time for reckoning is nigh. So, let's dive in. Good morning, everybody. Welcome to another, I was going to say another episode. And although it is now there is a series of videos on YouTube of our class, it is a class still. It still feels a little strange. Okay, welcome to another class of geometry. Okay, where just like science, it's not about why, it's about why not. Why wouldn't you want to explore this and just have fun with it? Okay, so speaking of exploring and having fun, let's take a look at our exploration from yesterday. Go ahead and open up your worksheet on tangent properties and check your work against mine. See how you did. And please, please, please ask me any and all questions. I'd be happy to explain them. I think one was pretty much right on the example that we did. 2 is a little bit of an extension there. And 3 takes it one step further, although part A, I guess, is directly applying that property. And then B is testing, oh, what do you remember about quadrilaterals more so than circle properties, but also relevant. So I will go ahead and point out that because you have the 2 consecutive right angles, okay, we know that from here over here is a perfect, like, complete U-turn. You've gone from this direction, turned, and then turned again, exactly 90 degrees. You've turned completely around, right? You've got consecutive interior angles that are supplementary. 90 plus 90 is 180. So that means PM and QN are, in fact, parallel, but that's the only pair of parallel lines we get, thus the trapezoid. Okay, and then here is 5 and most of 6. Can't quite get everything in view. There we go. And I guess that covers 4, 5, and 6 all there. Right. If you did not get this one, I would say the process looks at this point 39 to the origin. That line segment there is a radius of the circle, and thus you know is perpendicular to the tangent, right? All of these questions should somehow apply one of these properties that we brought up yesterday. So if you didn't use any of them, try to find a way to make use of that. Draw in a radius. You can always draw more lines. Okay? And now I know that this is a right triangle, but that doesn't really help me. But what does is from 0, 0 to 3, 9, I can find the equation of that line, and I know its slope is then the perpendicular, right, opposite reciprocal to find this one, and then I use that slope with that point. So you could also have this in point slope form as well. Number 5, how do I know that PA is congruent to PD, even though it's like 3 different sized circles in between them? Well, you go one step at a time. I know PA is congruent to PB because they're both tangent to the same circle. And I know PB is congruent to PC because they're tangent to the same circle. And law of syllogism there, right? This is congruent to that, and that's congruent to this, then PA is congruent to PC, and I know PC is congruent to PD, and so PA must be congruent to PD, right? Follow the chain of congruent to congruent to congruent, right? And then finally, number 6, making use of this internally tangent versus externally tangent. Right? The difference being you have one circle inside the other, touching there, and they're overlapping, so you would subtract their diameters, versus externally tangent. They would be outside, touching each other, and so you'd have to add the diameters, or rather, I guess you want the distance from the centers, so you'd be focusing on the radius, adding and subtracting the radii. Would be more accurate. Okay, any remaining questions on that guy? Point down, because my iPad's here. I should be like pointing there. And this over here. Channel Line or Vanna White. No questions here? All right, excellent. Then let's move on to today's topic, which is arcs. Not just for surviving floods anymore. Right? We can do all kinds of great things with the arcs of a circle. Not the whole thing. We're going to focus on narrow in part of a circle. And so first up, how do you create an arc? You take a slice out of the circle. Often it is intercepted by some kind of angle through the circle, either a central angle or an inscribed angle. We mentioned inscribed figures way back at the beginning. All right, that was an object drawn inside of a circle with all of its points on the circle. So as such, an inscribed angle is an angle entirely inside, but all of its points, the end points and its vertex, is on the circle, as opposed to a central angle where the vertex is at the center of the circle. It's in the name. Okay? And it turns out if you compare the angle to this intercepted arc here, the central angle, we well know, is going to be equal to the intercepted arc. I'm using equals there, not congruent. They're not the same shapes, but the measures will be equal. But the inscribed angle, let's say this is the same point C. Let's call this 70 degrees and this 70 degrees, right? So that means central angle ABC is also 70 degrees. But inscribed angle ADC is not 70 degrees. It is not the same as the central angle here. And I think if I was to draw that in, and then we capture and move it over, you can probably see, hey, it's definitely got to be smaller than, right? That's pretty clear. But exactly how much smaller? Turns out they are, in fact, precisely half of the intercepted arc. How's that for convenient? So that would make the measure of angle ADC equal to 35 degrees in this example. There. And that's the basis of it, right? That's going to set us up to be able to do all kinds of interesting things inside of a circle. And there's several consequences thereof, right? Expanding from that. Knowing that it will always be half, you could also say then that any and all inscribed angles that intercept the same arc. Okay, so if I was to draw, let's say, a completely different angle here, but it still goes to AC, right? Call that E. It also, by definition, it's an inscribed angle. It has to be half that intercepted arc. It's also going to be 35 degrees. So all of them that intercept the same arc are congruent. Okay? Every inscribed angle hitting the same arc must be the same measurement, because it's half of the same thing. And one step further, we also see semicircles pop up a lot. People love circles, and even more so, they love just half a circle. It's like one too much. I don't want a whole circle, just half is good for me. Okay? And when you inscribe an angle into a semicircle, think about that for a moment. There's, whoops, I need to draw here. Look at me, it's going to be kind of a parabola thing. So into the semicircle. What you're not seeing then is the other half of the circle. And so an angle inscribed there is actually intercepting that other half of the circle, which means it's intercepting an arc of 180 degrees. So it's half that, which means angles inscribed in a semicircle will always be (90 degrees right angles. Okay. We can add our little square in there. I missed. There we go, that's better. Right? Handy feature. And all of that comes out of half the intercepted arc. If all you know, inscribed angles are half the intercepted arc, just remember that fact right here. That's all you technically need. But down there in purple comes a couple handy shortcuts that are a direct consequence of this applied in specific scenarios. Gives us these convenient facts as well. Okay. Any questions there so far? No? All right, then let's move on. Arcs have measures. We've been messing them, right? We call it the other one 70 degrees, whatever. They also have a length. And so one point of potential confusion for students is the difference between arc measure and arc length. Two different but related things. So an arc measure is what we've seen already. That is always measured in degrees or radians or some version of angle, right? It's an angle unit. Arc length could be measured in meters or inches or feet, etc., any other length unit. Okay? So one good clue as to what you're dealing with there is what are the units involved? Is this the same units I would find on my protractor? Well, then it's an arc measure. Or are these the units I would find on a ruler? Well, then it's an arc length. Okay? Arc measure tells us how much turn in the circle, right? It's how much did you rotate around the circle? Because a circle, a full circle, right, it represents a whole rotation, spinning around. And the arc is how far along did you go there? How much turning did you do? The arc length tells us how much distance you traveled while making that turn. Okay? So it depends on the size of the circle. A little circle, the arcs are going to have a little arc length. Big circle, it's a big arc length because it's more distance to get around. Okay? Which means the arc length, you could say, is proportional to the arc measure. I'm going to add one here, and circle size. Right? What does that look like? It means how you calculate it is most directly, or definitionally, I should say, would be to set up a proportion of the two. The arc length as a fraction of the whole circumference, the whole distance around the circle. Right? that is the same fraction as the arc measure out of that full circle's rotation, aka 360 degrees. Right? So if you wanted to find the arc length, you could solve for that and set up a simple formula. You take your arc measure, divide by 360 degrees, and multiply that by the circumference, which is, as always, 2 pi r times the radius. That's it. That's all you need. There's the formula. Any questions on arc length? No? Okay. Then for today you have these 6 plus 6, 12 questions. Right? The first 6 dealing mainly with the interior angles inscribed in central and otherwise. And then the next set bringing in the length and arc length, right? So first, you're going to need to identify, okay, what is the radius? Here it's 6. What is the arc measure? Here it's 120. So I'll go ahead and set this one up for you, right? The length of arc AB is going to be, I want that measure of 120 out of the full 360 times 2 times pi, aka 3.14, good enough approximation for this worksheet here, times the radius 6, right? Run that in your calculator, see what gets out. Oh wait, nope, they say leave in terms of pi. I'm sorry, let's not do that. Let's just leave it here as pi. What does that mean, leave it in terms of pi? Pretend pi is like an x, right? You're just reducing your expression there. Leave it as x, right? Multiply, divide, all the other numbers, and leave something out in front. This will be equal to something, 4 pi, or whatever it is. 5 pi, 6 pi. I'm not sure how many pi's. Actually, 120 out of 360 is 1/3 times 2 times 6 is 12. 1/3 of 12 is 4. It is 4 pi. There you go. So that is how you will write your answer. Okay, I think I've done more than enough for you already. Final call for questions? All right, then I will leave you with the rest of the class time to work on those. Please ask if you run into any trouble.